Welcome back, everyone. The next session up is HydroGNSS Data Products. The chairs for this session are Serena Donati, Senior Systems Engineer and HydroGNSS Technical Lead at SSTL, and Max Pastina, Scout Missions System Manager at the European Space Agency. And I hand over to Serena.
Hello, everyone. Thank you, Ben. Let me introduce our first presenter of this session. That's Nazzareno Pierdicca, also known as Maurer. He's professor at La Sapienza, University of Rome, and is going to give us a presentation about soil moisture from HydroGNSS. Maurer, the floor is yours. Thank you.
Okay, thank you very much, Serena. Can you see the screen?
Yes, we can see the screen.
Okay, the full screen is okay. Okay, so hi everyone, good morning or probably good evening. My name is Nazzareno Pierdicca from Sapienza University of Rome, and I'm giving the presentation in collaboration with Emanuele Santi from CNR IFAC in Florence. This is about soil moisture, and I will review briefly the importance of soil moisture and the capability of measuring soil moisture from GNSS reflectometry, according also to past experience from the literature and also from our group. And I will briefly describe what we have done till now using artificial neural network to retrieve soil moisture from SIGNES and TDS data. And then, so the importance of measuring soil moisture is well known as a factor which partition the incoming radiation into latent and sensible heat. So there are different applications related, for instance, to the forecast of flooding, to the management of water resources, and to the initialization of numerical or assimilation into numerical weather prediction model, and of course in agricultural applications. So the application of GNSS reflectometry for land dates back probably order of 20 years, and there were different projects. These are a few examples studying this application for land since the application for ocean were already demonstrated in the past. So in blue there are few projects funded by the European Space Agency, in which the group that is involved in HydroGNSS, that is the Sapienza University of Rome, CNR, and the University of Regatta, were involved in the past. But of course, there are other initiatives from IEEC, from CESBio, from UPC, and others. So which is the principle we are able to measure soil moisture from GNSS reflectometry? Basically, it is the same principle of other microwave techniques, that is the content of water is affecting the permittivity of the soil. And so wet soil reflect more, especially in the near specular reflection, that is in the geometry of the GNSS reflectometry observation. Instead, soil roughness has also an important role in the signal that we are collecting, especially in near specular reflection direction. The soil roughness is going to reduce the reflection itself, and to introduce a diffuse term. And also the vegetation affects the signal, because mainly it attenuates the reflection and introduce also a diffuse signal due to volume scattering. So in any case, the sensitivity to soil moisture to the reflection to this to the reflection to the soil moisture is in the order of magnitude of the one of the other system, and in particular the one of monostatic radar, that is in the order of 1.5 dB in the average for a change of soil moisture of 10%. I'm referring to volumetric soil moisture. In case of very flat surface, as I will tell you later in more detail, the reflection from the soil surface is perfectly coherent. So in that case, the first Fresnel zone dominate the signal, and in this case, thus the signal comes from an area that in case of a spaceborne platform is in the order of 1 to 2 kilometers. In case instead, if the surface is rough, the signal is mainly a diffuse incoherent scattering. So in this case, the resolution is related to the bandwidth of the transmitted signal. And in this case, the resolution is in the order of 20-25 kilometers. The real situation are probably in the middle, and this is still a topic which is under investigation in the science community. But in any case, you can see that the resolution should be better than one that is now achievable from, for instance, microwave radiometer. Here, there is one of the first examples of the sensitivity of the reflection to the moisture, and this is a comparison between the change in soil moisture, which was measured by SMAP, and the change in the magnitude of reflection that was measured by SIGNES. And you can see that there is a very similar pattern, because both sensors are detecting the change in soil permittivity. The models to explain these sensitivity are available, and for instance, these are from models, the sensitivity of the reflectivity to soil moisture. This is in case of a flat terrain. We have to consider, however, that in case of terrain with some topography, the sensitivity is kept as a function of soil moisture, but the presence of topography is producing a bias between different, let's say, topography condition, so that it is clear that in order to estimate the soil moisture, we have to rely on ancillary data, which describe and provide information about other factors affecting the measurements from the sensor, which can act as a disturbance in the retrieving of soil moisture. And these factors are topography, small scale roughness, and as I said before, presence of vegetation. So we have to consider this factor and to try to exploit as much as possible ancillary data to compensate this effect. This is another example of a simulation, but in this case, this is the reflectivity as a function of the biomass in case of a flat area, or in case of an area with topography, but the biomass retrieval will be discussed in another presentation later. So there are many evidence, not only from model, but only from data of this sensitivity. And you can see, for instance, this is from a ground-based experiment, the sensitivity of the ratio between left and right polarization as a function of soil moisture content. This is a case of produced using Technodemos data compared with the soil moisture from SMOS. The sensitivity is clear, as I said before, about 1 1.5 dB for a change in soil moisture of 10%. There is a lot of scatter, of course, which is due to this, let's say, confusing factor that I was mentioning before, like topography, vegetation, and of course, incidence angle. Of course, there are also other factors that we still not know very well, because of course, some of this scatter in the point can be for sure due to calibration issues. So getting a very good calibration of the reflection is an important task in the mission, and also to noise of the in the sensor and the speckle fluctuation of the signal. It must be said that it has been demonstrated from data, but also from model, that getting data at two different polarization, that is collecting both the right hand and the left hand polarized reflected signal, may help to partially limit the effect of some of these disturbing parameters, and in particularly may help to limit the effect of the roughness in the collected signal. In terms of algorithm, there are already available different methods. There are work using simple linear regression approaches, or using empirical change detection approaches, or using more sophisticated machine data-driven approaches like artificial neural network. These methods have been trained and validated comparing the retrieval from GNSS reflectometry with the soil moisture retrieval from SMOS and SMAP, or from in situ data provided, for instance, in the frame of the International Soil Moisture Network. We are with the HydroGNSS, we are trying to add new observables to what is already available from Cygnus or from Technodemosat. And in particularly, as was described before, we are attempting to use also two polarization instead of just one polarization that is collecting both left and right. And we are also attempting to improve the resolution by sampling the signal at a higher rate and sampling both the amplitude and the phase of the signal, and also to collect data in other band, that is signal E5 or L5, that have a higher bandwidth. But of course, these are new measurements that we would like to exploit to improve the capability of GNSS reflectometry. But most of the goal of the mission in terms of thematic accuracy and resolution have been already demonstrated in the literature from let's say standard observation from Cygnus and Technodemosat. And these are some example of comparison of the retrieved soil moisture from Cygnus as a function of the observed soil moisture from SMAP or from in situ data, in this case using a change detection algorithm, in this case using a neural network, and in this case using a sort of empirical matching between SMAP and Cygnus from different authors. So in our work, we will use both methods, that is, we will start from a more simple algorithm which assume a simple model relating the reflectivity measured by Cygnus to the to the Fresnel reflection coefficient, which is the parameter which is function of soil moisture, but considering other confounding parameters, that is the attenuation due to vegetation. This is the vegetation water content, and the effect of the soil roughness, which decrease the reflectivity. So it is clear again that we have to rely on some ancillary data to be able to account for and to compensate for these disturbing effects. If we compute the logarithmic of this function, you can see that in this case we can assume a linear relationship between the reflectivity measured by HydroGNSS in decibel and the parameter that I mentioned before. Of course, we are going to exploit in a later stage also more sophisticated data-driven approach that is, for instance, a neural network. In this case, we will have as an input to the network the measurement from the HydroGNSS, not only the reflectivity, but we can also exploit different observables derived from the delayed Doppler map. That is, for instance, the shape of the delayed Doppler map that provide an idea of the amount of coherent and incoherent reflection, which may help in the retrieval phase. And also, as an input, we have to consider some ancillary data, for instance, a digital elevation model to account for topography. Then once this neural network will be tuned and calibrated, we will apply the neural network to retrieve the soil moisture. As for the type of product that we are expecting to achieve, I want to, as I said before, I want to show here again how the signal can be due to different type of mechanisms, that is diffuse scattering in case of rough soil. In that case, the signal is coming from a larger area that is about 20 kilometers, or coherent scattering from a very flat surface. In this case, the signal is dominated by this small area that is the first Fresnel zone. Based on this, we can assume as a requirement a resolution, a spatial resolution that, according to the type of reflection that we will observe, can go from 1 kilometer to 25 kilometers. I have to say that in most of the case, we will, in overland, we will have a diffuse type of scattering. So the resolution will be mainly in the order of 20 kilometers. In terms of thematic accuracy, we have a goal of 4%, which is common to other missions, like, for instance, SMAP, but a threshold of 8% can still be considered quite useful. With a single satellite, we can achieve, of course, full coverage of the Earth after 1 month, which is a limit of this mission, because this mission is going mainly to demonstrate that a constellation of small satellites can finally become a very suitable tool for soil moisture monitoring from space. And so we have done some exercise, of course, using neural network in collaboration with CNR, IFAC, and Tor Vergata University. We have considered the cygnus observables, and not only reflectivity, but also other parameters that can be derived from the delayed Doppler map. And we have introduced as an input to the neural network different ancillary data, like, for instance, CCI land cover, above ground biomass, and of course DEM and the slope of the surface. And we have used it as a target to perform a calibration of the net and final validation, both soil moisture from SMAP and also in situ soil moisture. These are examples in which the retrieved soil moisture is compared to the target one, that is in this case SMAP soil moisture. This is using only SIGNESS data. This is the results when we use, for instance, also CCI land use as an input. You can see that the results improve a lot by probably exploiting ancillary data, but the importance of SIGNESS is in any case very much significant, because if we use just ancillary data for retrieving soil moisture, we get very bad results. So these are the type of results that we are expecting using HydroGNSS. That is, in this case, you can see a root mean square error of about 0.05 and coefficient correlation coefficient of 0.9. It is quite good. Of course, we have also attempted the comparison with other independent data, that is in situ data from the International Soil Moisture Network. Actually, to get a good result, we have to filter the network which are more reliable. So if we, for example, consider the networks which were also used to validate the SMAP product, we get results that are quite promising. So for instance, this is a comparison of the retrieved soil moisture from SIGNESS with the soil moisture measured by a network in Walnut Gulch, which is a well-known site for soil moisture earth observation, soil moisture validation. And again, the root mean square error is in this case very good, and the coefficient correlation coefficient is 0.7. In other sites, we have also find quite promising results in terms of root mean square error. So at the end, this is a comparison of the map from soil moisture from SMAP in one day. We can see the SWOT of this radiometer, and these are example of a daily map from SIGNESS at a resolution of 5 kilometers on the left and at a resolution of 36 kilometers on the right. So we can conclude that it is time to assess the capability of a GNSS reflectometry to measure soil moisture near operationally from small satellite, that the methodology are becoming quite consolidated. Of course, we can always improve the result, hopefully in the next 2-3 years before the launch. The spatial resolution and thematic accuracy may be considered quite promising. HydroGNSS, in any case, will attempt to use a new observations that is dual polarization and high frequency channels with high rate and complex channel to even improve the performance if possible. And we are confident that HydroGNSS will demonstrate that the constellation of small satellite could be in the future a breakthrough in soil moisture monitoring in terms of cost of the full mission, and of course in terms also of temporal resolution, which needs for sure not only one satellite, but a constellation of the platform. And this is the end of my presentation.
Thank you very much, Mauro. That was very interesting. I'm wary of time, so I'll propose to move on to the next presentation. And if we can take any questions, Max, maybe we can answer them later at the end of the session. So let me introduce our next presenter, Kimmo Rautiainen. Hopefully I pronounced that correctly, or at least as close as possible to be a correct Finnish pronunciation. Kimmo is from the Finnish Meteorological Institute and is going to give us a presentation about freeze thaw from HydroGNSS Please, Kimmo, the floor is yours.
Thank you. Maybe the screen should be released so that I can share my screen. Okay, thank you. Can you see my screen?
Yes, we can see the screen.
Is it in a full mode?
Not yet, no. Now it is.
Okay, thank you.
Thank
you for introducing me. The pronunciation was good. Thanks. Yes, I'm Kimmo Rautiainen. I'm from Finnish Meteorological Institute, and we are responsible on the HydroGNSS Level 2 freeze and thaw processor. And we work in close cooperation with all the other science partners, and especially with Sapienza University, with Davide Comite and Mauro Pierdicca. I will now talk more about, in general, how to detect the soil freeze and thaw state changes using the GNSS reflectometry. Very briefly, first about the motivation in general. The seasonal soil freezing affects about half of the Earth's land masses, and 1/4 the land area are on permafrost regions. So globally, soil freezing and thawing have great impact on our environment, and they affect surface energy balances, water flows, and carbon cycle, as well as photosynthetic activities and microbial activities within soils. Due to the effect on hydrological cycles, soil freeze and thaw state is also included into the essential climate variable soil moisture product. As Mauro already explained about where this detection of soil moisture is basically based on, it's the same for the soil freeze and thaw changes and detecting them. These satellites operate at L-band frequencies, so we are measuring the L-band GNSS signal reflected from the ground, and at L-band there is a strong contrast in permittivity between solid ice and liquid water. So frozen soil has much lower permittivity than thaw soil, especially if it's in a moisture condition, and this can be detected from the forward scattered signal. It is also, the L-band is also a good frequency, as there is a fairly good penetration through vegetation layer. The algorithm development of the soil freeze and thaw detection for HydroGNSS mission is based on earlier studies that have been conducted, and on the work we conducted also during the ESA Scout mission concept and system consolidation study. For freeze thaw monitoring from obvious regions, the high latitude coverage of HydroGNSS is of course essential. There hasn't been that many previous studies on detecting soil freeze thaw changing using satellite observations of GNSS signals, and also for very obvious reasons, because there hasn't been such instruments available very much. So these are listed, the main studies performed on from this subject. 2 used a novel approach using the SMAP radar receiver to capture the GNSS signals, and the committee provided the first results on monitoring of freeze and thaw state using TechnoDemosat-1 observations. Then there was 2 publications from Wu and Karengo Luengo that published results using the Cygnus data over Tibetan Plateau and Andes Mountains. And then there's our recent publication where we actually reported the main work we conducted during this SCART mission concept and system consolidation study, and continued basically the work that Davide Comite started earlier together with Sapienza University. And these two most recent studies both use seasonal threshold algorithm to demonstrate the detection of soil freeze and thaw changes. And this is also the baseline for our HydroGNSS Freestyle algorithm. In the following slides, I'll present the results that we obtained during the system consolidation study with Tecno Demosat-1 data. The observable that we are interesting is for the soil freeze-thaw detection is the reflection coefficient at the specular point. That's derived from the measured delay Doppler maps. And with TDS1 data, our first task was to determine the dynamic range of the reflection coefficient between the frozen and thawed soil conditions. And for this study, we used as a reference data SMOS freeze-thaw product. We used the SMOS freeze-thaw data to define whether the TDS1 observation was originating from a frozen soil or from thaw soil conditions. And now we need to point out that TDS1 satellite was an experimental mission, and it was not dedicated for only for GNSS-R observation or the observations over the land areas. So there are limited amount of data, and there are large gaps both spatially and temporally during its mission. However, this the very important thing about the TDS1 mission was that the orbit included the high latitude areas, and as such it has provided very valuable measurements for example, for remote sensing of cryosphere. So for this, in this study, we divided the northern hemisphere to 4 large areas, and within each area we defined the mean reflectivity value for frozen and thaw soils based on this reference information we obtained from SMOS freeze-thaw data. And we defined these mean reflective values for low vegetation, land classes, and forested areas, and also divided the observations to based on elevation ranges to those below 200 meters in elevation and those from 200 to 500 meters in elevation. And here are shown the results for year 2017. The TDS mission was from 2014 to 2018, and each year provided pretty much similar results for these 4 areas. And the results are also pretty much as expected. The freeze-thaw dynamics are larger for low vegetation areas than for forested areas, and also the reflectivity is significantly higher when lower elevations are considered. So, encouraged by this previous results on the freeze-thaw dynamics, we wanted to demonstrate how the freeze-thaw detection with TDS1 data over the northern hemisphere works. So we used the threshold detection algorithm for this. First, we treated the TDS1 data to equal area scalable Earth grid, this EAST2 grid projection, and we had to use rather coarse resolution due to the limited amount of data. So the 1 pixel size is only 75 times 25 kilometer. And then we empirically defined the reference reflectivity values for frozen and for thaw soils, and they are shown in these two figures here. And then we set a pixel-wise threshold in between these two references, actually in the middle for this demonstration purposes. And then finally, we applied some temporal averaging. There was quite a lot of averaging required due to the limited amount of data, so we used 30-day of running mean. And then each observation was categorized either to belong to the coming from the frozen soil or from the thawed soil, based on whether the the temporal average observation was closer to the frozen or to the thaw soil reference. And here are the example maps for melting season 2018. Again, unfortunately, there was quite many data gaps, and so this was basically the only season that we were able to derive continuous maps for the whole period. So there is 4 maps from February, March to May, June, and there is the process of soil melting is shown here. The blue in blue color there is a frozen soil indicated, and in white color the thaw soil. So the soil melting is progressing as the time goes on. With hydrogenesis, we expect much improved results as there will be continuous measurements, and this is the aim and the objective is in land application. So it will be much better mission for this freeze-thaw detection. So almost in a final slide, I will quickly present the main steps of the hydrogenesis freeze-thaw algorithm that we are building or developing. So the main observable for us is the reflection coefficient at the specular point. We will study on how to use also other observables, and of course we need the timestamps and locations and so on. But this is the main observable that we are at the moment aiming and to use. And then the first step is to grid the data to ease-2 polar projection for some spatial averaging and for harmonizing the data for freeze-thaw detection. Still, we will need temporal filtering, even though there will be more data compared to the TDS. If there is one hydrogenesis satellite, then as Mauro said, there will be about 30 days to get the full coverage of the globe. With 2 satellites, it will be 15 days. So there will be the amount of temporal filtering that is required is highly dependent on whether this option of having 2 satellites is happening or not. And then after the temporal filtering, we will build up the pixel-wise references for frozen and thaw grounds. This will require some additional ancillary data, such as air temperature and snow extent, to verify that certain observation is possibly from the frozen ground conditions and from the thaw ground conditions. And finally, there will be the freeze-thaw detection and error estimation, and at the same time remove certain obvious errors, such as if there is during the summer period false alarms of soil freezing when there hasn't been any temperatures close to 0 degrees Celsius. And then the output will be provided in EASE-2 grid freeze-thaw information, and there will be a daily update for this. So the temporal filtering will be such that it will be in a daily basis. The whole northern hemisphere will be updated. So there's either running mean or some other temporal filtering that allows that. As a summary, can say that the earlier studies have demonstrated that the GNSS reflectometry is very suitable for monitoring of soil freeze and thaw state at high latitudes. So far, there hasn't been any dedicated mission over land areas at high latitudes. Only limited number of observations are available, and properly calibrated observations at high latitudes are missing. Observation from HydroGNSS will provide much more data and with much improved calibration, and this will be the first mission dedicated for land applications. And need to be pointed out that this data gridding at the beginning of the processor and the algorithm, it will play a large role in successful freeze-thaw detection. Okay, that was all I had to say. Thank you.
Thank you very much, Kimmo. Let's see if there aren't any questions or just move on to the next presentation. Yeah, let me introduce Dr. Estel Cardeilach from IEEC. She's going to give a presentation on forest. Sorry, just been told my mic wasn't set up correctly. I'll repeat what I just said. Let me introduce Estel Cardeilach from IEEC. She's going to give a presentation on inundation from Hydrogenases.
Hello, good morning, good afternoon. I will be sharing my screen now. Let me know if you don't hear me well or you don't see it well.
I can hear you, I can see the presentation, so thank you.
Thank you. I'm going to talk about the inundation, the surface inundation product from HydroGNSS. This is work conducted by the IEEC team in HydroGNSS. And well, the contents of this talk will be first to see why we need this type of measurements, what kind of HydroGNSS observables we can use to measure the surface inundation, an overview of the processor that we have in mind, and then a few more details about two of the processors that we are developing, and finally the conclusions. Besides rivers and lakes, land can be covered by water in wetlands, swamps, by human activity, and also by natural phenomena like flooding. Global warming potential of the methane gas is estimated to be much higher than the carbon dioxide, and wetlands are the largest natural source of this atmospheric gas in the world. It's the largest single contributor to the methane emissions. And the worst of it is the uncertainty. It's the widest uncertainty range in this type of emissions. It is estimated that by the end of this century, the natural methane emissions from wetlands are projected to increase. And overall, well, the rising temperatures, the higher water tables, thawing of permafrost all contribute to the increase of this type of surfaces, releasing more methane into the atmosphere. Another difficult aspect to monitor all this activity is that inundated areas might be under vegetation canopies, and then it's difficult to observe them, to measure from remote sensing platforms like satellites. And another important aspect is that wetlands are highly susceptible to climate change, leading to this wetlands collapse. This destruction could decrease the terrestrial water storage capacity. So a complete and consistent dynamic map of the global wetlands should be obtained as required by different bodies. Let's have a look at HydroGNSS observables. The observables suitable for surface inundation are two types of different HydroGNSS reflectometry observables. One of them are the power DDMs. These are incoherently integrated. They are power measurements, typically at 1 Hertz rate. So that means that the spatial resolution is at several kilometers level. But then one of the novelties of HydroGNSS will be the coherent channel. We call it this way, but essentially it's a single pixel information from each DDM, just one single pixel, complex data, the ENQ or amplitude and phase, coherently integrated, but not incoherently integrated. So it's very short time sampling, so high sampling rate. Initially for HydroGNSS, we are considering 4 milliseconds integration, and that means 250 Hertz rate. That increased a lot the spatial resolution at sub-kilometer level, even 100 meters level, how to say. And also we have the phase information, which is very important. Each of these type of products will be available at dual polarization, and it's being discussed if they will be also available at dual frequency or not. An overview of the Inundation processor. Essentially, all these processors have two steps. The first step is the detection of coherence, because the reflections of water, especially of calm water, such as the water in most of the inundation and flooding conditions, presents high degree of coherently reflected signals. And then a second step is to distinguish from all these coherent samples which ones come from water, because it's true that in some type of surfaces, especially if they are smooth and flat, they can also produce highly coherent scattering despite there is no water. In one case, the coherence detection is essentially an algorithm based in signal processing methodologies, while the inundation flagging is a bit more heuristic, empirically based, and many different factors, it's more complex, many different factors might affect, like the terrain, topography, slopes, the vegetation canopy, and so on. So it's likely that these empirical relationships and threshold values to flag the coherence as water or no water will depend on regions. The baseline algorithm will use the power DDM at left-hand circular polarized data, then apply a power DDM coherence detection algorithm, and finally a power DDM surface inundation flagging processor. And in parallel, there will be the coherent channel left-hand circular polarized data that will be fed into the coherent channel coherence detector, which is different from the power one. So then we will also need a different flagging process. This can be further complicated. For instance, combining the output from both the incoherent DDMs, the power DDMs, and the 200 samples of the coherent channel. Or we can also add the polarimetric data, so both DDMs and coherent channel at the two polarizations. Each type of observable will go through the coherence detector that corresponds, and finally we would need to flag independently all of them. Or finally, a combination of all these coherence indicators to flag properly the water presence. At the moment, we are in the baseline approach. So I'm going to present first the processor based on incoherently integrated power DDMs. And the first step, as I said, is a coherent detector, in that case based on power DDMs at, let's say, 1 Hertz, 2 Hertz. Our group has not developed our own algorithm. So what we've done is simply to select one of the published algorithms in the literature, in particular Alcaldi et al. 2021. And in this case, it's a simple algorithm, easy to implement, and that provides good results. It's a power spread detection, and essentially it makes the ratio between the power given in a core delay Doppler cells with respect to the power of the rest of the DDM, excluding the noise, the noisy cells, the floor noise cells. Essentially, that's the main basics of the algorithm. You can see more details in the paper. And the same authors have established a threshold to detect the coherence. So when this power ratio is above 2, we consider that it's coherent sampling. Here we have from the paper the power ratio for a given set of days in September 2019, and after applying the threshold at value 2, which is the coherent non-coherent, and that's our implementation of the same algorithm using the same data set. So we can see that it's validated against the paper. And what, as I anticipated, sometimes due to other reasons, we might have very coherent reflections in places where you don't expect any water. So what we've done is to check if other parameters like the terrain topography, the slope, the vegetation might help distinguishing these regions and to be able to provide thresholds at different regions depending on all these other parameters. This is work undergoing, but I'm curious. I wanted you to show this particular plot. This is again this power ratio that, as we said, starting at 2, so above 2 means coherent scattering. And this is the sigma naught also from Cygnus, or this is from Cygnus. And it's an example of the Amazon basin only. And we can see that in this case, for the coherent reflections, there is a relationship between the sigma naught, a very clear amplification of the relationship between the sigma naught and the above ground biomass, which is the color scale. So I thought that was interesting to highlight this, because that means that having information on the coherency of the signals, it's also important for the above ground biomass, but in particular for the methane studies, the methane generation, that could be interesting because all these points are likely to be on flooded conditions. And we can then assess not only the presence of water, but how much potential for creating new methane gases are there. So I think that can be interesting also for methane studies too. And then we are going to explain the processor based on the coherent channel, that is the complex data at high sampling rate. In that case, what we've done is to implement our own algorithm that was published first in this paper, Lee et al. 2021, but now it's also being included in other new papers. We call it the coherence coefficient. The multiplication by the okay, let's explain. A Z peak is 1 pixel of the DDM, of the complex DDM at the peak value. And that's the product of the complex conjugate, not by itself, but the next coherent sample. So after, let's say, 4 milliseconds, and divided by each amplitude. So essentially, this is a phasor, unity phasor, amplitude 1, that has a phase that relates to the increase of phase between one phasor and the next one after 4 milliseconds. The output for the level 1B product will be the 250 hertz, the real part of this coherent coefficient. If it's 1, means that there is no increase or decrease in the phase, both phasors are aligned. If it's 180 degrees phase jump, that would be -1, and all the rest is something in between. And also for the level 1B, we will provide the 1 hertz percentage of samples that has the real value of these coherence coefficients above a threshold. And then for higher levels, what we'll do is a further coherent integration of this coefficient, which is even more efficient to detect coherence. Let's have here an example of synthetic data that we've generated with a tone. in that case, 10 Hertz tone with some noise added. Here we have the plots for noise of 6 dBs, around 1.2 dBs, and below 3 dB, minus 3 dBs. And the three different colors, it's a different tone, 10 Hertz, 20 Hertz, 30 Hertz. This would be a pure tone at different Doppler residuals. And the gray would be completely random samples with no tone. On this axis is the percentage of samples in 1 second that have the CC values, the real part of the CC values, above the X axis. And what we see is that if we take as a threshold for this product, the 1 Hertz percentage, if we take as a threshold 0, we have that around 50% percentage corresponds to completely random time series, while it increases up to 100% when it's a pure tone with no noise added. So this is a good range, a dynamic range for identifying the degree of coherence in the signals at 1 Hertz ratio. And then when we further integrate coherently, the coherence coefficient, we lose a bit of spatial resolution, but then we have a really precise and clear idea of the coherence and the water. And we see here this example, one track. And we can see, for instance, this the transition between these water tanks, these water reservoirs. We can see that it's coherent in red and non-coherent in green, even if these are very small filters. This technique has been also validated. Again, this is the paper Lee et al. 2021 in the Mississippi area using Cygnus data, one episode with no flooding against one episode with flooding. And we can see the tracks with the coherence coefficients after some coherent integration of the order of 20 millisecond integration. And we see that when there is no flooding, the coherence is low. And then when there is flooding, the coherence is high, is in red. If we focus in these two regions correspond to regions with some areas of very dense vegetation canopy, up to 200-300 tons per hectare. And you see in region A, this one here, that would be the densely vegetated area. And despite the very dense vegetation, we see that the coherence is detected. And we also see that there are two roads here. So the road is dry, so you can see the dot, the yellow dot, that there is no coherence, no water on the roads. And similarly for this other region, region B, also with some areas with dense vegetation, and also around these dense vegetation areas, we still can detect the water underneath. That was not detected when there is no water. So the conclusions: HydroGNSS inundation processors are based on coherence detection. HydroGNSS provides both power DDMs at low rates and single pixel complex data at high sampling rate of the order of 250 Hertz. And that's what we call coherence channel. So the L1B and L2 processors implemented are for both types of observables. The power DDM approach is based on Alcaldi et al. 2021. The complex, the coherent channel, it's based on Lee et al. 2021. We are doing studies now to analyze this effect of the vegetation and the terrain slope. And so far, what we've seen is that in some areas, there is potential use of this coherence indicator for above ground biomass over water. And well, the coherence channel approach provides very fine spatial resolution, and it's proven to provide this flooding detection despite very dense vegetation canopies. And with that, I think I finish my presentation. Thank you.
Thank you.
Thank you very much, Estel.
Serena, I think that we have a few questions for Estel. Maybe we can give some live answer now. The first one is from Anania. and she was wondering if the PR is equivalent to signal-to-noise ratio.
It's not exactly equivalent because, in fact, the noise cells are not accounted for. So after you remove the noise cells from the DDM, what you compare is the power constrained to a limited area with the rest of power out of this area.
Thank you. Another question from Ricardo, and he was wondering which is the difference between the coherent reflection from a lake and from an inundated land, and how you can distinguish one from the other, basically.
Yeah, I think, I'm sorry, probably we did not use the proper wording. When we say inundation, we mean water. So it would be the same lake or a flooded area. Yeah.
Last question from Maria. What is the resolution of the map of the power ration shown in slide 19?
Okay. 19. Slide 19. The resolution. Oh, you got me here. I don't think we have applied any gridding. Or did we? If there is a gridding, should be the same as in the paper, because we tried to reproduce the results in Alcaldi et al. 2021. But now I don't remember. Sorry. But it should be in the paper.
Thank you again, Estel.
Thank you.
Serena, I think that we can move to the next presentation.
Sure. Thank you, Max. So let me introduce our next presenter, Emanuele Santi from Institute of Applied Physics of the Italian National Research Council. He's going to give us a presentation about forest biomass from Hydrogenases. Thank you, Emanuele.
Okay, thank you, Serena, for your kind introduction. And let me very briefly acknowledge my colleagues and the other people that was involved in different extent to the development of these algorithms and to the achievement of this result that I'm going to present. In brief, this study investigates the use of the GNSS techniques for the monitoring of the forest above ground biomass with the final scope of defining the concept for retrieval to be applied to HydroGNSS data to generate the level 2 above ground biomass product. Of course, we are waiting for HydroGNSS data, so the study focused on data from TechDemosat of SSTL and from the NASA Cyclone GNSS Cygnus. As first step of this activity, we evaluated the sensitivity to above ground biomass at global scale and also in some selected test sites that are representative of different forest types from boreal to equatorial. And there is in general a shortage of a suitable set of in situ measurements at the resolution useful for validating the product from GNSS techniques. So for as target parameters for developing the algorithms and for validating them, we considered the above ground biomass global maps from Earth observation. We also carried out some comparison with the L-band SAR to understand which are the advantages of bistatic scattering as GNSS with respect to the monostatic as a SAR. At the end, we proposed, we identified and developed a data-driven approach with an algorithm based on neural networks that has been implemented and validated by using both the Cygnus and TDS1. A quick overview of the dataset we used for developing this algorithm. Cygnus data in 2 versions and 2 time periods. That means version 2.1, 6 months in 2017, and version 3 from August to 2018 to June 2019. Just to have an idea on how many data we used we processed it for developing this algorithm. We considered the main observables from Cygnus dataset. We considered also, as said, the TDS1 data from the first period of Cygnus, April-December 2017. We considered some Allos pulsar time series on selected test area, and as said, we considered as a reference for above ground biomass the pantropical map by Avitabile, and also the European Space Agency Climate Change Initiative above ground biomass map, with similar results. We can say that we obtained more or less the same result. As ancillary information useful for the developing the algorithms, we consider also a global digital elevation model, the GTOPO 30, at horizontal grid spacing of about 1 kilometer, and the land cover, again, from the ISA-CCI land cover state, in this case, product. And we tested several aggregation at several resolution. In this case, the result I am going to present will be have been obtained at about 5 kilometers grid spacing. So let's move to the main result of the sensitivity analysis, local and global scale. This first scatter plot shows a comparison between the reflectivity from Cygnus and TDS1, plotted both as a function of above ground biomass, for the flooded tropical forest of Manaus in the Amazon River basin. And there is some offset, is about 80 dBs, depending on the different parameterization we used for computing the reflectivity, but the sensitivity, you can see that is the same, more or less the same. And also the correlation is about 0.4, is the same for both. Another interesting result was in comparing bistatic and monostatic scattering. This scatter plot shows the behavior of bescattering from HV polarization from halos on the same area, and the reflectivity. Bescattering is in blue points, and the reflectivity are the green points. For a dense forest, that means biomass higher than 100 tons per hectare. In this case, we can see that the reflectivity still keeps the decreasing trend with a correlation that is almost unchanged with respect to the other, is 0.4. While for this in this range of values, that means at above ground biomass higher than 100 tons per hectare, the bescattering loses almost entirely the correlation to the above ground biomass. There is some saturation effect, as also pointed out by the very poor correlation. Moving to the global scale using Cygnus, we of course we found a higher data dispersion. However, the expected decrease of the reflectivity is still confirmed. This is a density plot. That means that the colors are proportional to the data occurrence. You can see that the correlation slightly decreases with respect to the other, but the decreasing trend is still there. Another not negligible problem we had to manage is about the thresholding for low data at low signal noise ratio. And in general, the common value is about 2 dBs, and that in general for the other application, data for having a signal noise ratio lower than 2 dBs are discarded from the analysis. Here you can see a coverage map obtained on the Angola test area. Is a sample area we identified for this application. On 10 days basis is the result, the color is proportional to the number of overpasses in the 10 days. And this result has been obtained for signal noise ratio higher than 0.5 dBs. Here, the scatter plot of the signal noise ratio is a function of the above ground biomass. And if we use an higher threshold for signal noise ratio, that means we use the commonly used 2 dB threshold, this is what we get. You can see from the comparison from the of the above ground biomass distribution in this image below that with the 2 dB thresholding we lose almost entirely the coverage on dense forest. However, if looking at the sensitivity of the reflectivity, we can see that some sensitivity is still there also for a signal noise ratio lower than 2 dBs. So the most effective solution we found by using the machine learning algorithms was to relax the threshold for signal noise ratio below 2.5 dBs and include the signal noise ratio in the algorithm inputs. Moving to the algorithm implementation, we focused, as said, on neural network, and in particular, we considered the multi-layer perceptual neural networks trained with the backpropagation learning rule. Inputs were several. We tested several combinational GNSS observables and ancillary parameters. The output was the above ground biomass. We implemented an iterative systematic search of the optimal neural network architecture in terms of number of neurons and in the layers to prevent overfitting and underfitting. In short, the training is repeated a given number of times by starting with a very simple neural network and increasing each time the number of neurons and the hidden layer, and also exploring the different transfer function between linear 10sig and log-sig. The output of this process is the, let's say, optimal neural network for the given problem in terms of highest correlation coefficient. How we managed the data set for training and validation, we starting from the data set available, we by random sampling divided the data set in 2 parts. The percentages changed between 50 and 50 for training validation for local retrievals, and we arrived to 10% for training and 90% of data for validation in global retrievals. The training set that is used for training the network is further sampled in the 60-20-20% to have the training, the 2 independent tests at each training iteration. After training, the network is saved and applied to the remaining part, that means the validation set that has not been used for training, in order to get the validation result of the algorithm. This is a very first example of above ground biomass. This was obtained from TDS1 for the area of Manaus. In total, we had about 5,000 data, and we divided in 50-50 and assayed. And this density plot shows the estimated above ground biomass by the neural network as a function of the target from the pantropical map on the validation set. That means more or less the alpha is the 50% of the data available. Moving to the global, again, we validated against the subset of the above ground biomass map, and we explored the different combination of Cygnus observables and ancillary parameters. This result on the left is the estimated above ground biomass as a function of the target by considering the Cygnus and the land cover information. The central panel showed this result by also including the topography information. We can see that there is an increase of correlation and a decrease of root mean square error. And the panel on the right shows the result obtained by exploiting all the available information. That it was the best result we obtained. And we also implemented a configuration without Cygnus data, just to verify if there were not some, let's say, apparent relationship that have been exploited by the network. But of course, we didn't get any successful result in this. This sort of saturation that mainly affected the first 2 plots not necessarily is depending on the training on training issues, but it could also depend on problems on the pantropical map. You can see here that the same saturated behavior is shown in this plot, in this density plot that represents the above ground biomass from pantropical as a function of the same quantity from the ISA-CCI. And you can see that the same set of data at very high above ground biomass are saturated as in the result. We also exploited the most effective parameter observable, the most effective observable for this application. We found that the reflectivity is the main driving observable for the above ground biomass retrievals. And adding the training age and the other observables, we didn't obtain any significant improvement. Here you can see on the left the result obtained by considering only the Cygnus reflectivity and the ancillary data, and on the right the same, but considering including all the other Cygnus observables. And you can see that the correlation, the root mean square error, don't change at all, practically at all. Okay. As a further application, we attempted to compare our result with the error requirements established by the Committee on Earth Observation Satellite, CEOS. And in particular, for above ground biomass, the error is established should be less than 20% or less than 10 tons per hectare for above ground biomass lower than 50 tons per hectare. So in this density plot, is shown the error in percent as a function of the target above ground biomass. And in red is the error line, is the threshold set by CEOS requirement. In green is the fitting of the data. We can see that more than 70% of the retrieved above ground biomass meet the CEOS requirement, but we have more problems with the lower above ground biomass than higher because of the effect of the other surface parameters like soil moisture and the surface roughness. Of course, we expect to improve significantly this result by exploiting the advanced characteristics, including the dual polarization, dual frequency of HydroGNSS. So a few examples of maps in the short remaining time at local global scale. Here, an example of above ground biomass map. On the right, on the left, the one obtained by neural network using TDS1 data, and on the right, the reference from pantropical map. Both are at 0.05 degree resolution, and we can see that although the TechDemosat was a demonstrator mission that didn't acquire continuously data, the full coverage of the area was not achieved considering the 6 months that data period we used for this analysis. This fact could suggest that a second satellite could be advisable for the HydroGNSS mission in order to improve the coverage. Here, the above ground biomass maps, on the upper left, the one from Cygnus, upper right, the reference pantropical, and the lower panel, there is the absolute error. Okay, in summary, what we can say is that, of course, the feasibility of using global navigation satellite reflectometry for retrieving above ground biomass was already established and is confirmed by this study. The reflectivity is, in our understanding, the main driving parameter for the retrieval, and the other observable that should not add much to the accuracy, with the exception, of course, of signal noise ratio. For signal noise ratio, that for which we propose to relax the threshold, the 2 dB threshold commonly used, down to 0.5 dB, and also using this observable as input of the machine learning algorithm. The ancillary information is, of course, effective in increasing the retrieval accuracy. The result using only GNSS observables are not so good, and are still satisfactory, but not so good. And concerning the spatial resolution, the results presented here have been obtained at the 5 kilometers resolution. High resolution up to the 1 kilometer that is the goal for HydroGNSS mission seems feasible, also because of the possibility of averaging long data periods and also to the slow biomass dynamics in forested areas. Of course, the second satellite could improve this. Concerning the targets, we didn't find any clear dependence of the error in the retrieval on the land cover forest type. Although depending on the latitude limits, the analysis of using the global analysis using Cygnus was mainly limited to a broad-leaved forest, of course. Concerning the retrieval range, as pointed out also by the comparison with the monostatic SAR data, the saturation is barely evident also in equatorial forest. And some more problem exist for low above ground biomass, and it could be reduced by including the soil moisture and the surface roughness in the algorithm inputs. This is feasible for the HydroGNSS target resolution, 25 kilometers, but these datasets are currently unavailable at 1 kilometer resolution, so this solution is not valid for the goal resolution. In any case, as already said, we expect a significant improvement thanks to the HydroGNSS advanced characteristics. And that's all from my side. Just me acknowledge that this activity has been carried out in the mainly in the framework of the ESA GNSS Overland and the ESA ecology projects. Thank you.
Thank you very much, Emanuele. Max,
Thank you very much.
do we have any questions?
Yeah, maybe we can ask, because Emanuele, you talk about the 6 months worth of data.
Yes.
And we were wondering if you can elaborate a little bit also on short-term measurement, so to observe faster dynamic observables on forests.
Okay, this the 6 month is refers to the what is has been defined in the mission requirement document, but the algorithm has been conceived to let's say to estimate directly the pixel by pixel, so to give an estimation of above ground biomass for each reflection point, for each specular point, for each data acquisition. So is only just because we set this requirement, but it should be not a limiting factor. Okay. The algorithm can estimate directly point by point the above ground biomass.
Thank you. Another question is, do you have any comment about measuring the above ground biomass data through a P-banded synthetic aperture radar?
Yes,
and HydroGNSS?
Yes, the idea could be to complement, for instance, the biomass mission. That is one of the reasons that pushed us to define a 6 month revisiting for this kind of data. I have here, for instance, we could complement the biomass P-band in USA and Southern Europe. These are 2 examples of a biomass map for this area that are not covered by biomass mission. And using Cygnus, in this case, of course, we are limited by the latitude boundary, but this limit that doesn't exist, doesn't affect the HydroGNSS. So a complementary product by merging the SAR, P-band SAR and GNSSR could be for sure feasible. and possibly with the advantage of a better sensitivity of GNSS set for the higher biomass values.
Thank you. Maybe one last question from myself, because you showed more than once that thanks to the innovation of HydroGNSS, the dual polarization, dual frequency, we improve many of the parameters of the measure, and you also talk that for the biomass, 1 kilometer spatial resolution is possible. Can you give us an idea of what is a common resolution now, and which is, just to understand
yes.
how better we can do with the HydroGNSS with respect to what is available at the moment?
Okay, I said the maps I've shown in this presentation have been generated at 5 kilometers resolution, and their validation referred to this. Is difficult to say in advance, to quantify exactly, of course, the contribution of the dual polarization, dual frequency. So we expect that it will contribute, but of course we don't have a data set to assess this. But so we are confident for the moment. And concerning the availability of data, if your question refers to the general
Yes.
availability of above ground biomass data products, what we found for now is the availability of some above ground biomass maps that are in general the resolution of around 1 kilometer, but the main limitation is that in general they are only static maps. So that means that not update or revisiting is foreseen. This is valid for instance for the geocarbon map. This is a global map. Is valid for the pantropical map, and also the map above ground biomass map on the ICE-CSIC data portal are updated not with such frequency of 6 months or higher. There are the last one, if I remember correctly, referred to 2016 or 2017. So it is definitely useful for following the biomass dynamics. It is this approach.
Thank you very much.
You're welcome.
Yeah, thank you, Emanuele. I'll introduce our next speaker and also last speaker of this session, Guiseppe Foti. He's Senior Research Scientist at the National Oceanography Center. He's going to give us a presentation about ocean-based level 1 calibration, ocean winds, and sea ice products from HydroGNSS. Please, Giuseppe, the floor is yours.
Thanks, Serena, for the introduction. I will try and share my screen. I actually recorded my presentation to make sure we keep the time. I hope it works. Okay, just let me know in case you cannot hear it or see it. Can you see the screen now?
I can see the screen.
All right, let's see if it works. Hi, everyone, my name is Giuseppe Foti. I work for the National Oceanography Center. I'm going to be talking about ocean-based L1 calibration, quality control, ocean winds, and sea ice for ESA HydroGNSS. I would like to acknowledge my co-authors, Matthew Hammond and Christine Gomen-Ginger. Outline of this talk. So we're going to talk about the level 1 processor for HydroGNSS, which includes also submodules for quality control, also for data anomalies and radio frequency interference, and of course also for ocean-based calibration, and an example of application of this approach to NASA Cygnus version 3.0. And then we're going to move on to the level 2 processors for HydroGNSS products in terms of ocean winds and sea ice extent, and then we will finish with a summary, of course. So we start with the quality control at L1, and looking at TDS1 data, we found that in some cases there are sequences of anomalous DDMs. You can see the plot on the right showing an anomalous band of high power right in the middle of DDM, which is clearly not a physical effect, and this renders the estimation of the SNR quite problematic. So we developed an automatic flagging algorithm, which is based on the power density across the DDM, and this has been integrated in the NOC L1 processor. So on the bottom plot, you see examples of these anomalous tracks, and it's possibly something which is attributable to correlator anomalies in the onboard processing system. Okay, next we have another submodule which is dealing with quality control, and this is to do with radio frequency interference. And it is well known that RFI can contaminate GNSS returns, and this clearly directly impacts the inversion process and diminishes the quality of the retrieval. RFI typically exhibits a high spatial temporal variability, so a number of studies have been trying to address this problem by using a statistical characterization of the noise floor for automatic detection, and using kurtosis as a metric, and thresholds around the Gaussian value, which is 3 around the noise floor, to try and detect these radio frequency interference. We tried these approaches. We found that it's not always successful in detecting RFI contaminated data. So we have developed a new detection algorithm, which is instead using the shape of the DDM itself. This is a bit a comparison. So you see on the left the distribution by kurtosis of true positives, so data which has been checked manually, which contains RFI for sure. And you can see that there is a significant amount of data where the kurtosis is lower than 3, and it's actually contaminated by RFI, and 44% of these cases are with kurtosis below 4. So the approach we are suggesting is more robust, but also offering a better detection performance compared to the traditional, if you wish, kurtosis approach. This approach has only been tested on this kind of RFI, so with this kind of shape, with these vertical bands in the DDM, and not on other forms. So there is no guarantee that the performance will be better than kurtosis approach on other forms of RFI. Okay, it's ocean-based calibration. So this is still level 1, and we developed the baseline scheme, which is called the GNSS a posteriori calibration for TDS1. So the scheme is based on accumulation of ocean reflected data, and does not require, there's no requirement for data incoming from the Zenith channel. The scheme is able to address systematic effects, including variability of direct power across different GNSS transmitters, and also geometry, both from the receiver side and the transmitter side. It cannot really tackle high frequency effects such as power jumps and attitude fluctuations. So the performance will largely depend on the data volume which is collected over the oceans and which is made available, and the training duration will also depend on that. So it's usually a trade-off between accuracy and training duration. Okay, this is a diagram giving more details about the processing chain within the L1 calibration processor. So starting from the left, we have L1 uncalibrated data. First step is to estimate the SNR, and then implement a number of radiometric corrections. And then there is the first submodule, which is dealing with receiver end corrections in terms of azimuth and elevation, so geometry from the receiver point of view. Then there is a further module which is implementing transmitter end corrections in terms of SVN, so GNSS transmitter, but also geometry as seen from the transmitter point of view. And finally, we get to L1 calibrated data. Okay, this is an example of application of the NOC processor to Cygnus data. So we have in the left plot a single bi-static configuration, so using a single receiver, which is FM05, and a single transmitter, which is SVN43. And on the right plot, we have the same receiver, so still flight model 05, but this time receiving signals from SVN50, so a different transmitter. So we fixed the wind field, the wind speed to be around 7 meters per second, and ideally the sigma naught field should be homogeneous or quasi-homogeneous. Instead, we see at least microscopically, we see that there is a clear bias between the two maps, and that there is a global bias in any location. But even using a single bi-static configuration, so a single pair of transmitter and receiver, we see that there are quite prominent geographical biases. And we have found that these are due to residual geometry effects, which are not being shown. Then we applied our calibration approach to this data, and this is what happens. So if you see that, you can see that the bias between the two transmitters has been largely removed, and the geographical biases are less prominent, but they're not gone. So there are possibly other factors which are intervening, which are not being addressed by our calibration process. But overall, we can say that the picture is quite significantly improved. If I just switch back and forth, you will appreciate that. Okay, so then we move on to L2 products for HydroGNSS. So we start with ocean winds. And this is the approach we use at the NOC, which has again been developed for TDS1. It's called Calibrated Bistatic Radar Equation Algorithm, or in short, CBRE. On the left, you see a scatter plot of sigma naught versus training data from ICE-CSIC. And you see on top, which is the GMF we are using, the geophysical model function. And we are using an exponential of two factors, sorry. Okay, once you fit that, and then you see on the right the validation plot instead, which is the output from the algorithm, so on the y-axis, and the verification data again from ICE-CSIC on the x-axis. And you see that well, the validation then shows that the performance of the algorithm has a bias of around 0, close to 0, and an RMSE of around 2 meters per second. It's important to notice that these are metrics which are average over a range of 0 to 20 meters per second, but there is quite some variability across the range, so it's not constant. Okay, so I will show you then an example of retrieved wind field from TDS1 on the left, and verification data from ER5 this time, so not ICE-CSIC. And you can tell by eye that there is quite good agreement between the two fields. And if you compute it, you find that the bias is within minus 0.5 and plus 0.5 over 3.5 years, which shows that the performance of the algorithm is quite stable in time. Okay, so finally we address CISX10, another L2 product of HydroGNSS. And here you see on the left plot a typical waveform, which is incoming from the ocean, and on the right you see a waveform which is instead coming from sea ice. And it is well known that sea ice typically exhibits a stronger coherent scattering component than the ocean. And essentially at the NOC, we have developed an algorithm which is using the shape of the integrated waveform to classify sea ice and ocean. So the algorithm is based on the evaluation of multiple slopes around the peak of the waveform, and then it's been tuned using ERA 5 data. So it's based on thresholds, and then I will show you next the performance of the algorithm and how it performs in the Antarctica. So this is a map of sea ice detected by the NOC algorithm using TDS1 data on the left, and on the right you see the equivalent sea ice field from ERA 5. It's easy to see that the similarity is quite striking, and by computing it, we found that the agreement is better than 98%, which point is basically not really easy to tell which one of the two is performing better or is having some shortcomings. Okay, so that's about sea ice. And finally, a summary. This was all to say that the NOC is leading the processing for the HydroGNSS ground segment for L1 ocean-based calibration, also quality control and flagging, and also L2 products in terms of ocean winds and sea ice extent. And the baseline calibration scheme was developed for TDS1, but we have tested it now for with NASA Cygnus, and preliminary results are quite promising, which demonstrates that it's applicable also to other missions. And this concludes my presentation for today. So thank you very much for your attention.
Thank you, Giuseppe. That worked quite well, went very smoothly.
Right on time.
Right on time, yes.
Well done.
There are unfortunately no question from the public. Maybe I can ask. Okay, wait. There is one question from Paolo. Have you got any sea ice result of the Arctic?
We do. I just didn't show it in the interest of time. The agreement is above 95%, I believe, in the Arctic, for some reason which have to do just with the distribution of land. But yes, we do have results in the Arctic as well.
Another question from Emin. Do you have any idea how to which is the origin of the RFI?
Well, I'm not really an expert of RFI, but this is RFI that we are seeing after a matched filter, a GPS correlated matched filter. So it's RFI of a very specific form, which is going through an L-band matched filter GPS. So it's possibly RFI, which is targeted at these kind of navigation systems. But again, I'm not best placed to answer this question in detail.
Last question is basically on the difference between the calibration scheme of HydroGNSS and Cygnus.
Again, I'm not directly involved in the calibration of the Cygnus mission, so I'm not entirely sure of all the details behind their strategy. But the strategy that is going to be used for HydroGNSS is very much based on the approach that we developed in the course of the years with Tech Demosat1 at the NOC. I hope that answers the question.
And I think that this is it for this morning, Serena.
Yeah, yes, that closes the second session for today.
Thank you very much.
Thanks, everyone.
Thank you.